Welcome to another episode of The Brand Called You, a podcast and video show which brings you role models sharing their leadership lessons, knowledge, and experience and wisdom from hundreds, if not thousands, individuals from around the world. If you're new to the channel, please subscribe so you won't miss a new episode. I'm your host, Frits Bussemaker, and today I'm going to have a great pleasure because I'm going to have a conversation with Bob Coecke. Bob, welcome to the program.
Hello.
Allow me to introduce Bob. You are a Belgian theoretical physicist, a professor in quantum foundations, chief scientist with Quantinuum, but you're also a musician, performing and recording since the 80s. You are retrospectively being called the pioneer of industrial music, and you're also one of the pioneers linking quantum computing in music. So again, Bob, welcome to the program. And
Hello.
let me first start with a statement, because we're going to talk about quantum mechanics. What is it? And sort of, how did you come into the world of quantum mechanics?
That's an interesting story. So when I first went to university, I actually was studying engineering and architecture. And then this to some extent has to do with the fact that I'm coming from a small village, and I didn't grow up in the big city, so I had a kind of different perspective. But after a while, I had to do some internship in the real world for this engineering job, and I felt that the real world was nothing for me. So I decided to become a scientist. Another part of becoming a scientist, I thought, is staying at a university or something like that, going to make it easy for me to play music too. So one of the courses I got in engineering was quantum mechanics, because it's just a standard course in engineering, and I hated it. I thought it was just terrible. It was more like a cooking course than actually trying to understand anything.
Okay.
And,
Explain now what that means, a cooking course.
So basically, the way it was taught, and there is an historical reason for that, which goes back to Feynman, that he told people, I mean, he didn't really say that, but people interpreted what he said is nobody can understand quantum mechanics. So the result was most of the teachers said, okay, don't bother.
Okay,
And
just to confirm, this you're talking about Richard Feynman.
Richard Feynman, yes, the Nobel Prize, yes.
Yeah.
And so this meant that all these teachers interpreted that we should just present quantum mechanics as a bunch of kitchen recipes. Like, do this when this, then do this when that, and just don't think what you get. Don't think about it. So it was horribly presented. You couldn't, I'm a very sort of visual person who wants to imagine things, and there was no effort done whatsoever to actually give a picture of what it is. Now, I mean, so when I had to decide which discipline I wanted to do, I said, okay, I'm going to change quantum mechanics. Why not? That's a nice challenge. I know people have tried this since the originator of the language of quantum, John von Neumann, which is the father of modern computer architecture, of game theory, of many scientific domains. And he himself built quantum mechanics, but he wasn't happy with his own language. He wasn't happy with his own language. So that I took as a challenge. I said, I'm going to dedicate my career to that. But under the hood, so I choose for quantum physics, under the hood, I wanted to fund my music career. So at some point, I got PhD funding to do a PhD. And the system was such that the money was pretty much all accessible to me on day one. So half of it was spent on day one on a music studio. And then it was like beans in tomato sauce for the next couple of years because I spent all my money. So yeah. So that's basically I got into it. I must say, at the time, thinking about what quantum mechanics is about, what it means, was a very unpopular subject. There are reasons for that. I can get into that, but it was a very unpopular subject, which meant that after my PhD, I was unemployed. And then I had to sort of rebrand myself first. I did this as a mathematician and logician. Because of a miracle and many sort of rounds around the world, I ended up at Oxford University, where a few years later I became a full professor. I mean, my title was Quantum Foundation, but it was in computer science department. It was in a computer science department, because in the physics department at the time, it would have been completely impossible, given the subject matter. Like I just said, it was very unpopular in physics. Now, to qualify that statement, 2 years ago, we got a Nobel Prize, which was exactly about that sort of domain, the foundations of physics, like with Zeilinger and oh, come on, I'm missing the names, but yeah, the 2022 Nobel Prize, which was about quantum non-locality, like and other mysteries about quantum mechanics, which were then experimentally shown. So the world has changed since then. That subject of foundations of quantum is now very big. It's a very big subject. It's a very prominent subject. It's tightly intertwined with quantum computing and quantum technology. And I mean, so my goal, which I initially set to change quantum mechanics, I kind of started doing this properly with success in 2003, 2004. I had some attempts before which were taking me in some direction, but the real breakthroughs were 2003, 2004 when I was at Oxford University.
Okay. Now, can you maybe take the audience along? How relevant is quantum going to be for the general public, for the population?
I mean, it already is. It already is.
Okay.
Because without quantum, we wouldn't have this conversation. The reason being, like the transistor, which is like the basic building block for all our information technology devices, our phones, our computers, and all that, couldn't exist without quantum. And there's many other such things, but I think the transistor is probably the most important one, given our life, the form our life has taken these days, and that's already quantum. Now, the big change, which is about to happen, is rather than using quantum to build a building block for your traditional computer, like your bit, what people call a bit, inside your computer, in the new wave of stuff, which is quantum computing and related things, you're actually using the quantum system itself as the basic computational building block. And of course, because of what people refer to as quantum weirdness and all the special stuff, behaviors this quantum system has, this enables a bunch of stuff that there's no way you could do this with a traditional computer. And this has to do with communication, this has to do with computation and many other things, even things like sensing and we will completely, I mean, the sort of clocks we have now, which allow to our GPSs to work, they're only enabled by quantum. They're atomic clocks. So they rely on the properties of quantum mechanics. Otherwise, our GPS phones and stuff like that wouldn't work nowhere near as accurate as they do now. So quantum is already present, but it's going to become much more present very soon. And it's probably, it's going to change many things. It's going to change like things like drug discovery, like the way we, at the moment, for example, drug discovery is try and error. Or people go to some tribe in the Amazon hoping they have invented something we never came up with. The reason for that is the subject of drug discovery and many other things in chemistry is basically chemicals. Now, what can we do with chemicals? We can try to compute stuff about that. But that only works for very small chemicals. If you take something like a coffee molecule, which is not very big, we have all the equations. We completely understand how a coffee molecule works. We know everything about it. There's nothing to be discovered in terms of science and equations about coffee molecules. Unfortunately, we can't compute anything about this because computers can't deal with chemicals which are too big. And too big means quite small.
Yeah.
The reason for that is chemistry is all about quantum. The description of chemicals, the equations are all quantum equations. And quantum equations are very hard to put on a traditional computer because they blow up exponentially. That's, I mean, blowing up exponentially means like very quickly you're talking about all the particles which make up the universe. That's what exponential means in terms of things growing very fast. I mean, people learned a little bit about exponential during the COVID pandemic because there you also had these exponential blowups of like 1 case into like an entire population. So the thing is, if since it is a chemical, and you can actually compute this much better on a computer which would have been made up of quantum systems, because then the computer is native to the problem. The computer itself allows for exponential blow of your chemicals and all that, because it blows up exponentially itself in its capacity. Now, just because we mentioned Feynman before, so this observation was first put forward by the same Feynman, Richard Feynman. the fact that if you cut something which is quantum mechanical, like many materials, like chemistry, then the only reasonable way to compute things with it would be by a computer which is itself quantum mechanical.
Got it. Now, I understand that reading up on your background, you met Feynman, you discussed quantum with him.
No. I didn't meet Feynman. That was a joke. That was a joke from a Dutch comedian.
Okay.
On the other hand, like we are now having a fireside chat. A few weeks ago, I had a fireside chat with Roger Penrose.
Oh, Roger, yes.
For the Nobel Prize winner in Barcelona. You can actually find this somewhere on YouTube, I think. So those, of course, were similar conversations about AI and all that. So I'm also friends with Zeilinger, the one who got the Nobel Prize for the non-locality and all that.
Okay.
And he has been a big fan from day one, from the manner in which I actually changed the quantum mechanical language.
Yeah, because I want to talk about that. I was looking at an article in The Guardian, which was, well, like a good news article, quite provocative, where you said that kids understand quantum mechanics better than postgraduates.
Exactly. So what's beneath that is something, I mean, I mentioned the day 2003, 2004, which I've been working on. So what I've been working on is a new language for quantum, entirely new, but which has a very special feature that it is entirely made up of pictures. Now, these pictures are not illustrations or anything like that. They are formal mathematics, but they look like they look like a little bit like Lego, if you want to. It's a little bit like Lego even. It's not Lego. It's a bit different because you can't build quantum systems with Lego. But but interestingly, because I just mentioned Penrose from this fireside chat. So he was the first person, probably in the 50s, in the late 50s already, when he was still an undergraduate student at Oxford, to realize that some areas of math, some mathematical languages, formalism, can be replaced by pictures. And he did this as an undergraduate student when he was studying general relativity. In general relativity, there is some ingredient which in the mathematics which is called tensor symbols and things like that. And they're like horrible to work with. They have lots of indices and things like that. They're a complete mess. And those you can actually replace by pictures. That was the first observation of anybody who had done that. So Roger Penrose, and this is of course something which got mentioned in our fireside chat because that's where we connected up. Now, the surprise is that from this starting point of Penrose, you can basically take all of quantum mechanics and turn it into pictures. And so that's what we did. And it took me and many others like at least some 15 years to actually get to a first book, which told the entire story. This is not the book which the Guardian article writes about. It's a previous book, which was a university level course which I gave at Oxford University. That's what that book was. Now, what the Guardian article was about is that you can actually get rid of any kind of mathematical prerequisite to do quantum mechanics. The only thing in the way we have written the book now you need to know is angles, which, as far as I know, in the UK are taught at ages 6 or 7. So that's the only math you need to know. Something that starts at the age 6 to 7. What is an angle? Like, what is an angle? Like on a certain. That's all you need to know. We could even get rid of that, but we thought, okay, like 6, 7 seems to be a good age to start with. We don't have to go down really. So basically, what we did. So okay, there is this new formalism which is starting to become widely used in a quantum industry. So people who are building these new quantum computers and stuff like that. It's used by big companies, just to drop some names like IBM and Google, and of course Quantinuum, which is actually now the biggest quantum computing integrated quantum computing company in the world where I work. So we're all using this for many different things, but we want to there is a thing with science, and Max Planck, the inventor of quantum, said the following. So he's the first he actually coined the word quantum because he made an observation to say, realizing that whatever physics was in the 19th century, where physicists actually thought that physics was finished. And Max Planck, when he was a student, was told, don't do physics because we're done. So he basically observed that like some very essential things were broke. And that's where quantum came out, and then later relativity came out. So all these physicists were completely wrong. And there is something about science and physics that it changes very slow, and that people are incredibly conservative about making changes. So Planck said, science progresses a funeral at the time. So in order to come up with a new scientific idea, you pretty much have to wait for the previous generation to die out.
Okay.
That's a bold statement, but that's something we experienced ourselves. Physicists were very resistant to replacing their symbols and everything they studied so hard for, and which is so hard to basically learn because it's very advanced math by pictures. They were very resistant to it.
Okay. Yeah.
So we wanted to basically embarrass them, if you want to, by proving that they were all wrong, that this was the right way forward. So we thought, high school students, these were UK high school students for legal reasons, and they were quite randomly selected. We taught them quantum, and they outperformed postgraduate Oxford University students in terms of averages on an Oxford University postgrad exam. So this basically proves that pretty much everybody can learn quantum.
Okay, but does this also mean that, I mean, my assumption now is that people, the postgraduates know too much, are stuck in their mental model, how to look things, and the younger people generation are still open to ideas, so can absorb.
I completely agree that there will be an aspect of that to it, for sure. And this is something we will try to demonstrate very rigorously, because it's a very important point. And I think so basically, what did physicists, when I started to present these things, like going a long time back, what the physicists try to do, they try to translate this to what they already know. Now, this translation is very difficult. It's not an easy translation. So they actually experience this as actually quite hard rather than easy. While these young people, they take this on face value. And my experience with young people from ages going like from say 14 to 18 is that the younger ones, they have to be motivated, otherwise you can't do anything.
Yeah.
But the younger ones, if they're motivated, they seem to even absorb it quicker than the ones who are already 17, 18 years. Because in a way, these diagrams are an entirely new kind of mathematics, which is completely different from the development of mathematics over the last 2,300 years or something like that, 2,400 years. Because the way we have been taught in science and mathematics and science in general is to understand things in terms of how they are made up. So in medicine, the big breakthrough was anatomy, like seeing like what's inside the human body and what are the parts and how they play together to make a human body work. In physics, it was particle physics. You look for small particles and then try to understand everything by putting these particles together. In mathematics, it was something like elements and sets and collections of things. So from points, you start to build bigger things. And it's everywhere that people have approached science like that. And that goes back to Democritus. One of the ancient Greeks. And for physics more specifically, there was also in the ancient Greeks, there was like a kind of a pre-Socratic. So this is even before Socrates, and definitely before Plato and Aristotle and all that. There was like this dispute between Heraclitus and Parmenides. So Parmenides said, we're at every moment of time, we're in a static picture, the now. And then the progress of time is just a stack of pictures, one after the other. And physics has been set up like that, especially since Newton and all that, that you first take a picture of all the static, and then you come up with some equation which says, this is the next picture, this is the next picture, this is the next picture. Now, Heraclitus thought very differently. He said, we're in a constant flux. We're in a constant process, ongoing process. And so and effectively, these pictures are representing processes. They're out, and it seems that people are not used to thinking these terms. Like scientists are not used to thinking terms. So what do you substitute how are things built up out with? You substitute it by how are things related to other things. This may sound very complicated, but this is exactly what these pictures capture. It's about the relationships between things. like we having a conversation. I mean, what's not important now is how are you made up and how I made up and how what the differences in our genetic code. That's not really what's making the story here today. It's a conversation, the relationship we are setting up in terms of exchanging words. And this is not a weird idea if you think about it from like a sociological perspective or many
I
things.
mean, I'm immediately thinking of a picture says more than 1,000 words, so it's a
Yeah.
nice way to
And
describe an idea.
but so these pictures do capture something
Yeah.
quite and then and I mean I mentioned democracies like how things are built up. I mentioned the process view, and then the flux, and then there is of course this relational view, and this was actually emphasized by a person most people will name the name of Schrödinger. So Schrödinger is known for a cat, I think.
Yep.
Most
Cat.
also for people who have a bit studied like an equation, a certain equation, but he also put forward an idea that the most important thing about quantum mechanics is not what I mentioned the name von Neumann earlier. Von Neumann said the most important thing about quantum mechanics is observing something. What happens when you observe? You disturb. Things may change when you observe and all these sort of things. So he said that's not the most important thing about quantum. The most important thing about quantum is what happens if you bring two things together. When you bring two things together, then new things emerge which cannot be traced out back to what this is and what that is. So the idea of understanding things and how they are built up doesn't work anymore. You understand? Because new bridges are built between these two things, and that's exactly captured by this relation. And these pictures which we draw exactly capture these bridges. They're about these bridges between things, and it's the simplest way to talk about anything
Bob,
like that.
yeah, Bob, we're definitely going to include a link to these pictures. I assume they are available online, so people.
Oh yeah.
Okay. And I was just wondering, during this discussion, you so passionately talk about quantum, and I was just wondering, what's your inspiration? Are these the people you just mentioned? Is it the idea, the concept of quantum, and what it can do? What inspires you?
Uh, I think so. Initially, you mentioned that I'm also a musician. I also used to be a painter, so I've always thought of myself as an artist as well, even more initially than a scientist, and even today. And I think the particular sort of approach we took was very much artistically. I got actually quite a lot from, although I dumped my architecture career, I got quite a lot from that, from thinking about shapes and forms, because that's what you learn there, an entirely new way to think about substance. And that helped me a lot in the development of this pictorial language, actually. And then another thing which actually inspired me a lot is just being different, doing what nobody else does. From
Uh, you're fully aware of that. I would assume that if people would look at your picture, not in a million years, they would assume you are a professor in quantum fundamentals.
Yeah.
Is this something you do deliberately to provoke, or
I haven't changed my clothes since I was 15-year-old. So,
yeah,
well, I sometimes change them because they just rot away from my body. But,
it is style, yeah.
I mean, it's always been my style, pretty much. And I was like you mentioned, I played industrial music. It was sort of, you dress in
Okay,
black,
so
and all that, and it,
so the lesson there for me is even if you want to perform, if you become a professor, you don't have to conform to the, I'd say, a general accepted image. This is what a professor should look like.
It's a good question, because on the one hand, like I studied at the university, Free University of Brussels, it means definitely. So the free is different than, for example, the Free University of Amsterdam. The
Yeah.
Free University of Amsterdam is a religious university. Free University of Brussels refers to Freemason. It was an atheist, an explicitly atheist university. But I remember at 2 occasions at least, I've had remarks for how I show up at an exam.
Mm-hmm.
So I became an Oxford professor. I never had any remarks on how I show up in formal dinners. So it's an interesting thing that different cultures take this different, and what people would conceive as a very formal place as Oxford University also tends to be a very eccentric place. And people are eccentric in different ways. You can be eccentric through your mouth, you can be eccentric through your actions, you can be eccentric to your looks. And there I've never sensed any problem whatsoever.
Yeah. Okay, and brings me to another question. I mean, as you're in, I know you're in your house right now, but it looks like you're in a bar downstairs. I know that at Oxford you've
I'll
also.
show. So yeah, this is a
Yeah,
bit of a music studio.
yeah,
You see a guitar collection, you see a drums and all stuff like that. Yeah, so,
great.
so this
And
is
the
this is
first,
my
yeah. So is there is this also I mean and creating actually building your own bar in Oxford? I mean I'm now making assumption it also allows you to create an environment you're comfortable in, and when you're comfortable in, it frees up. Is that
well, exactly. I mean, and comfortable can be in terms of the space you're inhabiting. Comfortable can be basically your lifestyle of your
yeah,
life. You're imagining. I mean, some people are basically, uh, especially some mathematicians, they're like totally autistic about maths and they can't think about anything else. And some of them are highly successful. This would not be a life that is possible for me. I couldn't be sort of autistically isolated just doing science. And I think the sort of science I did, and that's more or less your previous question, was greatly impacted by that attitude that I didn't do science in isolation, but also related it to stuff in the outside world. Like, for example, the sort of relational stuff about how things relate is very much connected to like how you compose music. Like in music, when you see traditional music notation, you got a bunch of lines, one for each instrument with notes on it. And then you got a bunch of, if you got like an orchestra playing, there's a bunch of these. There's no connection between these different instruments. If you look at the notation, they're just, there is no wires connecting them. While obviously in the composer's head, they're all very intertwined. So this implicit intertwinement you have to do when you compose music yourself. You have to create this in your head, and that gives you a certain way of thinking about the relationships between it. And that's why this relational thinking came so natural to me. So because I'm doing all this other stuff, and like I mentioned, the architecture and visual stuff like painting, this inspired a lot the way I do science. I probably wouldn't have been the person to solve a problem that some people, I mean, there are people who get these like equivalent to Nobel Prizes for maths, and then they spend 20, 30 years on one problem. Huh? I mean, that would never have been something for me. That would never have been something for me. That's sort. So scientists. So you can have different styles of scientists, and they probably relate to the different ways they also are in real life. For example, there was this very big problem solved by Perelman, a Russian mathematician, and he refused all the prizes. He got millions and stuff like that in prize money for solving that problem. He just refused everything because he thought he was going to mess up his life. He's just living with his mom, and he wants to just live with his mom in the same lifestyle, because otherwise he would stop doing the maths as he wants to do it. So people insist on maintaining this sort of lifestyle environment to do the particular kind of thing we do. Now, in my case, the interesting thing is like I said, I was doing all this music. Doing music has inspired my science. But then recently, as you mentioned, I was also part of the first team who actually used quantum computers to generate music. So that's where things really came together. And I'm hoping this summer, I'm talking to a couple of bosses of very big festivals in Europe, very big festivals, uh, to basically be the first to have a band playing like music which fits in the festival, like which is not just like weird stuff, but which also involves quantum computers live. So that's what we're hoping for this summer. And I'm talking to people. Actually, the first time we met, I think after we had a conversation, I actually had a conversation with a boss from a very big festival in a country, you know.
Okay, well, let us know when that's going to happen, because I'm definitely be interested to come and listen to it. Time is running so fast, Bob, at the moment. Maybe one last question before we go, unfortunately. What's your advice to young people out there? So look, how do you start? What do you do?
Start like in science or in life or anything.
In life in general, you picked science as a career. How did you?
Well, I mean, do where you fit, do whatever makes you feel natural. Do whatever makes you feel comfortable. Don't be too intimidated by the world out there and what they tell you to do. Of course, you have to, I mean, this is the context in which you live. So we are not an isolated thing which live in the vacuum. We're people who live in the world and actually are being And that's quite related to what we were talking about. Our being is not just what we are made up from, but how we relate to this outside world. So the outside world is a part of your life. And it's a part of you, but the relationship you want to establish with it, just do it so that you feel comfortable.
Great advice, Bob. Bob, thank you so much. Hope you will continue to make great music and help the world understand quantum. You've made me curious. I'm going to explore. So I really enjoyed our conversation, and let's hope we can continue this in the future. Thank you so much.
Okay, thank you, Fritz. It was enjoyable.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the Brand Called You.